take it away.
Thank you. So, just like Alex said, this is the topic of the last 3.5 years of my life. So I thought a lot about this. We recently just gave a tutorial on this topic at the Biz conference in Vancouver. So these are fresh slides, and so let's get started. So multivariate networks, despite the kind of scary name, they're pretty predominant everywhere. The most common example are social networks, but they also exist in other contexts, like biological networks, where metabolic pathways are of interest and how those things connect, and also things like communication networks, or the very well-known Internet of Things. Right? So let's take a closer look at a specific example to see what makes these networks multivariate. This is a social network. And obviously one of the most important components is the topology, or the edges, how these people are connected. Well, what makes a network multivariate is the fact that we also have, for each one of these people, information about them. And we have things like how old they are, what their GPA is. We have all different kinds of things that describe the nodes in our network. So just as like a formal definition, a multivariate network is one where we have both the structure of the graph itself and then attributes on both the nodes and the edges. So how these people are connected is an attribute. Are they friends? Are they related? Or so forth. Now I'm showing you the attributes for one person. If we zoom out and consider that we actually have attributes usually for all the people in a network or all the nodes in a graph, you start seeing one of the biggest challenges in visualizing these, which is this trade-off between visualizing the topology and visualizing the attributes. What happens is that when you choose the efficient encodings for one, it usually comes at the cost of another. So for example, let's suppose we want to minimize edge crossings, which is the default force-directed layout. So that what that will do is it will compromise where we can place those nodes as a function of attributes. So you're kind of choosing topology over attributes there. If you decide to place nodes according to attributes, which I'll show you in one of the techniques called attribute-driven positioning, you end up with a lot of edge crossings, and so it's harder to read the topology of the network. So overall, that is the biggest challenge with visualizing these. So in order to understand what are the current approaches to visualizing MVNs, and I'll say MVNs and MVNV a lot, multivariate network visualization. We surveyed 205 papers, starting from 91 up until 2018. And all different kinds of papers. Technique papers, which are the ones that propose a new layout or a new way of looking at things. Evaluation papers, which are the ones that evaluate those techniques. And application papers are the real world, usually called design studies, but they're actual applies to real people with real problems. So with these three and all these papers, we published a state-of-the-art report that came out in Euroviz. So this was last year, the year of publication was 2019. We published this, we presented it this past summer. And the main contribution of this is this typology. Organizes all the different ways you can visualize MVNs into these different layouts, which we're going to be going through today, and also operations that you can do, both on the layouts themselves as well as in the underlying data. I want to give you kind of an idea of what we're going to cover today as this form as a little XKCD style map. So the layouts and operations are the typology that I just showed you. I'm also going to give you a more real-world application. You want to use one of these techniques. What do you use? What are the libraries out there that you can use? Talk a little bit about what are the kinds of tasks. So what are people doing with these multivariate networks? And last, I'm going to show you a website that will give you guidelines on if you have a certain type of data, if you have a certain type of task, which kind of visualization should you use. So let's start off with the tasks. So some of you might be asking yourselves, how is an MVN task different than just a general graph exploration task? There is a lot of work done on graphs in general and how they're explored in different tasks. The key thing is just like MVNs are topology plus attributes, MVN tasks are those that rely on both the topology and the attributes of the nodes and edges. So I'm going to give you 3 quick examples to show you what are MVN tasks. This is me. And these are all the people that I have published with as of this past summer. Now, for those of you who don't know me, I used to be an Arctic oceanographer before coming to the field of CS. And so maybe looking at this network, I might want to know who have I published with from my previous life in oceanography. Now, in order to answer this, I both need to know who's connected to me, so who I've published with, but I also need to know the attribute of what field they're in. If you had that information, you would know that only 2 of my collaborators from my past academic life are people I've actually published with. Now this is for nodes, attributes on nodes. Let's suppose that for each one of these edges, we also know how many times this collaboration has happened. So thicker edges means these people have published together more, thinner edges means they've only published once. And then with this network, I might want to know what is the cluster of authors that has the highest number of combined collaborations. To answer that, A, I need to identify the clusters with its topology, but I also need to add up the value of these edges to say which ones have collaborated the most. And in doing so, we would see that Niels, Mark, and Alex are prolific collaborators, and they've published amongst themselves very frequently. The last example of an NVIDIA task is a different network. So here we have places as nodes, and the roads that connect them are edges. And we have the following attributes on each one. We know that for every road, we have the speed limit that you can go, and for every business, you have their business hours, when they open, when they close. So let's suppose that we have an instance of the traveling salesman problem, where I want to start at home, stop by the bookstore, pick up some lunch, and then go to work, right? And the question is, what is the most efficient way that I can complete all these errands? In order to do that, I need to know what are the roads that exist between these points, how fast can I go on them, and when I get there, will the place be open or closed? So these are all things that rely on knowing both the structure and the attributes of the nodes themselves. So if we revisit the last three examples that I just gave you, what they have in common is that they rely on the structure of the network as well as the attributes of the nodes and edges. Now, when you have these tasks, they can be applied to different parts of the network, so what we call topological structures. So the simplest example is a single node. So an example here would be, find me the person that has the most publications, right? We don't really care about the connections, just the node itself. That would be a single node target. Slightly more complex are the neighbors. Find all the people that are connected to me that are from Brazil, for example, and so forth. So you get progressively more complex. Paths are really a common structure of interest in networks. So for example, what are all the Europeans on the path that connect me to a certain collaborator of mine, or so forth. Clusters, sort of like the example that I gave earlier, which loosely just means nodes that are highly connected amongst themselves. And then lastly, we have either the entire network or maybe a subset of that network, but here they're what we call overview tasks. What is the average number of publications in my entire network, and so forth. I want to describe a little bit the types of things that characterize a network. So at this point, I've used the word topology a few times, but just more formally, it is the structure of the graph, related to edges and how these things are connected amongst themselves. Not only that, if you look at nodes themselves, we can have attributes on each one of them, right? So here's an example where we have their name, their age, their nationality, and their GPA. We can also have attributes on the edges, like type, or how many times that interaction has happened. Now, this is stuff that usually comes with the data itself. Another thing we can do with networks is derive new attributes based on topology or vice versa. So for example, let's suppose here that I want to compute how many nodes this person is connected to, so the degree of that node. That is a topology characteristic of the node, which we then derive into an attribute of the node itself called the degree. We can also create topology from attributes. So let's suppose that I now want to connect all the people who are Brazilian. So I took the fact that this person is Brazilian. Can you guess that I'm Brazilian? And all of my examples are Brazilian. You connect people who are from the same nationality. You're creating topology from attributes. So the concept of topology and attributes can be a little bit fluid if you think that you can take one and merge them together and vice versa. Another thing to keep in mind when we think of networks are the types of nodes. We can have more. All of the examples I've given so far, people of nodes. But let's suppose we have a network where you're connecting people to the movies they've acted in. And then in this case, what really makes it interesting from the visualization perspective is that these nodes have different sets of attributes that describe them. People are described by their name, their age, their nationality, and their GPA, for example, while movies might have a title, a genre, and how much money was spent on it. Network size, and I just wanted to find these terms here because I mentioned this yesterday, if any of you were at my Viz seminar yesterday, using the term large networks, especially in a scientific computer where you have sizes people where large means a lot more than 1,000 nodes. So just kind of to set the stage here, when I say small networks, we're talking about under 100, medium 100 to 1,000, and large networks are over 1,000 nodes. And I'll use these terms when we get to the guidelines where I'm saying for a large network, use these kinds of things. This is kind of the stuff I'm referring to. And the last kind of, I'm going to say boring stuff before we get to the really cool demos, is these different types of networks. So in the space of what we call complex networks, we have sparse or dense, and those are pretty self-explanatory, what they mean. We also have layered networks, and the definition here being that all of the nodes in a given layer only connect to the layer next to it. So all of these only connect to this one to this one, this one, this one. So a real world example of layered networks are family trees, where for the most part, maybe not in Utah, genealogy, people only connect to the generation below them. And lastly, we have trees. Yes?
I was just going to ask a question about the size of networks. We can do that after.
Just I finished this, yes, one second, yes, absolutely. And trees are those where the rule is more strict than with layer networks. Trees, all nodes can only have one parent, right? And so trees are a more strict type of a layer network. Yes, there.
Can you meaningfully visualize large networks, like more than 1,000 nodes? I thought 100 is.
No, you're absolutely right. So with the sizing, we kind of talk about those that you can, when it comes, you can use attribute-driven positioning, and I'll talk about those where it's like a scatter plot, but not on the node itself. Okay. The most limiting technique is the on-node encoding because you need space to visualize the network with stuff on it, and we will discuss that when we get to it. So I'm going to give you an overview of the typology or the taxonomy of layouts that I showed you before from the state-of-the-art report. So this is divided into the top layer is pretty much the different types of ways that you can visualize in VNs. Node link layouts, tabular layouts, and implicit tree layouts. These are think of these as like the base playing cards. And then we have operations that will combine them and use them in different ways. So we have view operations and layout operations. And I want to take a moment to distinguish between these two because the name isn't inherently intuitive. So we use view operations for anything where there is a separate view for the topology and for the attributes. And there's different degrees to which they're put together. Juxtaposed, they're just put next to each other. Integrated, they're more one-to-one mapping. And the overload, they're on top of each other. But they're still separate views. When we talk about layout operations, we use actually multiple layouts to show topology or to show the attribute. So we have the small multiples where we repeat the layout for each attribute. And we have the hybrid where part of the topology is one technique and part of the topology is the other, and I'll talk a little bit about why you don't want to do that. And the last thing here, which is the data operations. Now, this is not comprehensive as far as data operations, it's more of the most commonly used ones, but we wanted to include it because a lot of times when you see a visualization, we have to remember that it is a result not necessarily just of the visual encodings that the author chose, but also of what they did to the data before they visualized it. So you can filter the data, you can aggregate. Everyone from a certain country now becomes a super node and so forth. These are all things you do to the data, and then you apply one of the layouts from the top row to get to your visualization. And I'm going to show you a quick example of how data operations can affect the final visual, but doesn't change the technique that you're actually using. So let's think of these blocks, and let's see how they play together in a very simple example. So we'll keep this here to the left as I go through the example. So the simplest, yet perhaps most common way of visualizing the VNs is on-node encoding. So here, and I'll talk a little bit more what that is, but here you just imagine that these nodes are colored by a certain attribute. So whatever that value is reflects onto the color of the node. Now we're going to apply a layout operation to this, which is the small multiples, and I want to see 3 different attributes for the same network. So now I have one view for each one of the attributes. I can apply a view operation. If you recall, what I said about view operations is that it has separate views for topology and attribute. So that will look like here is I extract out the attributes into a table, and I keep the topology in a node link diagram. So now you have these juxtaposed views. And lastly, I'm going to apply a data operation that will filter out one of those elements. So there is a difference to your final visualization, but it's still using juxtaposed views. You just apply a filter to the underlying data. Okay, so we're going to start and go through these different, I'm going to use examples for each one of these techniques. And to do that, we're going to use a sample network. Very simple network with, I think, 5 people. So this is Abby. She's kind of our main character there, and she is John's mother. She is also dating Tom, who is friends with Mark, who is married to Sue, who's also friends with Tom, who's co-workers with Cole, who is John's soccer coach. Okay, so these are like the very simple players, and what we're going to do is we're going to take this network and we're going to represent it in all the different ways so we can see the pros and cons as well as how you go from one to the other. Now, like I've said a few times already, the thing with these networks is we not only know how these people are related to each other, but we also have information or attributes on each one of these people individually. So in this case, we have their name, their favorite beverage, and how many times they've consumed that beverage in the past 3 days. So a pretty simple example, but for the sake of visualizing the different techniques, that will suffice. And then we also have information for, like we were saying, the connection between these people. So we know what type of connection that is, and we also know how long that's been going on for. So if you think of this in an attribute sense, we have qualitative attribute, and then we also have a quantitative one. And we have this information for all of the people in our network. So keeping this in mind, we're going to start with the node link layouts. And there's 3 of them, and the way that we initially separate them out is one of them is topology driven. So like the name implies, the layout here is defined only by the edges, only by the connections. No attribute goes into defining where these things are laid out. Versus those 2, where in different ways, the attribute defines the positions of the nodes themselves. Because the topology is the only thing that determines where these nodes are placed, the only place left to encode attributes here is on the node directly. So for lack of a less creative name, we call it on-node, on-edge encoding. So all the attributes get put directly on the node, and as we were saying earlier with Daria, that does limit the space and the number of nodes you can have on your screen, because it needs the space to encode directly on the node. For the attribute-driven variety, we have the attribute-driven faceting, where you have different boxes for different types of nodes, and we have attribute-driven positioning, where the actual position of the node is determined by an attribute. So starting with the on-edge encoding, we're going to go to our characters here in our social network, and we're going to place them and draw the nodes. And the layout here is determined usually in order to minimize edge crossings. There's a lot of different variants of this. There's an entire field of graph drawing that is devoted exclusively to what is the most aesthetically pleasing way of doing this. What is the way that we'll say put things that are closer together that are relevant in some other way. But for the sake of just what it means to be topology driven, it just means that we're minimizing the number of edge crossings here. As far as the attributes for the edges, we can add labels that describe how these people are connected. And then we can also encode, like I showed you in an early example, the width of the edge can encode how long these people have known each other and had that relationship. Now notice here, for the sake of this example, we have some edges that do not have direction, and we have the mother edge and the soccer coach edge, which have a source and a target. So this pretty much covers the common ways that you encode edge attributes, and you can think of the label of the names as a node attribute, but we usually have more than just a single node attribute. So let's take a closer look at how to encode attributes on these nodes. If you have a categorical attribute, a really nice way of doing it that's very intuitive from a perceptual standpoint is color. So we can use that for the categorical attribute, and then we can use the size of the node for the quantitative attribute. So if we were to say how many movies has this person gone to, bigger for more movies and smaller for less movies. While this is very perceptually effective, it's limited to 2 attributes. So let's suppose you have more than 2. One way you can do it is with these nested encodings. And I'll show you a real-world example, especially in biology where they do this a lot. But for a simple example, we can think of little bars where we have 1 bar for each quantitative attribute. And then here we can have, for example, a separate flip for a categorical attribute. So like I was saying, the most common use of on-node encoding is in the field of biology. So here we have a paper from Gallenborg who does a review of systems biology. You can see all different kinds, from the simplest just encoding with color to more complex nested bar charts or line graphs and things like this. One thing I want to point out, as I showed these examples, on the right here there's a bar where I put the glyph of the technique that this example uses, and sometimes it uses more than one technique, or sometimes it uses a data operation as well. So I kind of keep track of that on the right to show you how visualizations are often the product of combined data operations with view operations. Another really common use of on-node encoding are for aggregates. So for example, here, if you think this network has actually been aggregated from that original network, right? So here we have migration patterns in the US, and each box represents an area of interest. And so here the author took each one of these boxes, aggregated all the nodes, and made that encoding on the right. So they have a lot of information to show for each one of these these aggregate nodes. So in this case, on-node encoding is really nice, and you can leverage different types of visualization techniques like scatter plots or parallel coordinates to show a lot of information for one specific node. Here we have an example where they use images on the nodes themselves. Right, so this is from Mari graphs, and they have images that they're interested in this hierarchical tree. So they actually replace the node with the image itself. These are all examples of node encodings. I want to show you just 2 quick examples of edge encoding. So this is from BIS Explorer, where the edges represent the length of non-overlapping DNA. But these lengths can get really long, and in order not to have this layout take up too much space, they use this kind of squiggly encoding, which you can quickly detect the ones with the higher frequency are the longer ones, and the ones with the shorter frequency are shorter. So this is encoding an edge attribute by actually changing the way you draw the edge. Here we have a technique where several attributes are placed as bars directly on the edge. I didn't really find any real-world usage of this. This is more of a technique paper, but it does show the possibility of showing more than just the two that I've shown you so far, which is width and potentially color of the line itself. So overall, the on-node encoding is the most used, and therefore it is the most easily understood by most users. And it works well for all types of networks. There's no network. Some of these representations don't work well, only work for trees or don't work for others, but this is one that actually is suitable for all kinds of networks. It is not very scalable, and so this kind of addresses what we were talking about earlier. As you can imagine, unless you have a really, really wide display, you quickly run out of screen size. And the more you try to put into a node, the bigger they get. And if you maximize the size of these nodes, you're completely covering the underlying topology, making it very hard to see the structure. And because MVN tasks usually rely on understanding the structure and the attributes, you really end up hindering the ability to perform them efficiently. So overall, when it comes to recommendation, we recommend these for small networks when very few, usually under 5, attributes on the nodes are shown, or if you can use an on-demand zooming and filtering. So this will be the equivalent of a data operation where you say, okay, I don't have space for my entire network, so I'm going to filter out and just put 10 nodes that I'm interested in, and then zoom out, pick another 10 nodes, and so forth. And that's another strategy. Okay, so for this was the one where, even though it's the most commonly used, it has a lot of restrictions. So let's talk about how we can use the attributes to position the nodes themselves. I'll start with attribute-driven faceting. If you recall from earlier in our little sample network, each one of these people had a favorite beverage. So let's suppose that we want to group them by their favorite beverage. And what we can do is create kind of what we call a facet, but just an area on your plot for each one of these. And then what we do is we place the people within their facet. So here are the people who drink port, beer, and Coke. One thing I want to point out with this is the only thing that is determined by this technique is what the facet that these nodes fall in, but the positioning of the nodes within them is still free. So you can either use another technique or you can use something that's topology driven, like I want to minimize edge crossings within a given facet. So if you look at this layout and then you compare it to this layout, they're still faceting and they just optimize for different things. So this is kind of like the small example. Let's look at the paper that actually introduced the technique, which is Ben Schneiderman's semantic substrates. So here we have a data set where you're looking at port cases. So supreme port, the facets are supreme port and circuit port. And if a case mentions another case, then there's an edge between them. So what you can see here is that you have here the user selected 2 nodes, and you can see all of the edges that kind of go between facets. You can imagine that without this filtering, if you were to plot all the edges at once, you'd have a lot of edge crossings, which would make it very hard to interpret the structure of the network. So this is really helpful to understand, for example, do cases in a certain port often reference cases in another port, right? So when you have tasks that relate specifically to what you're faceting on, it's very useful. But the cost of that is you're introducing a lot of edge crossings. So one of the things that you look at on the right here for the data operation is going to show up that is very important for this to work is you need to be able to query and filter to only show the edges of interest for this not to become overwhelming. And notice here that on top of the faceting, that this technique also is using on-node encoding, where each node is also sized by the number of ports, the number of edges that it has. So you can kind of get a glimpse. If you see a really big node, hey, this one has a lot of edges, I'm going to click on it to then explore more. So this one actually uses faceting, on-node encoding, and the data operation querying and filtering. Another cool example I want to show you is one that facets in a slightly different way. So this is a group in a box where you have a US Senate co-voting network graph. So if the Senate members, Republican is red, Democrat is blue, and if they vote the same on a given issue, there's an edge between them. And so the approach that was taken here is that they ran a clustering algorithm, and for every cluster, they put it into a separate facet, but they're organized using a tree map layout. And so the plasma membrane, the cytoplasm, and so forth, and then you have the metabolites that live in each one of those. So when you're looking at this, even though you might be generating, because you're placing things according to where they are in the physical real world, and not necessarily according to the edges in the network, you are generating extra edge crossings, but they help the semantic interpretation if your questions relate to these layers, right? So this kind of leads me to what this technique is very appropriate for, which is networks that have these different node types, and that the attribute that is categorical, or what we call set-like, is important to your analysis, right? So that it will help you answer the questions you have related to these different facets. It's really not as scalable to in respect to the number of nodes, or for really dense networks. And like I said earlier, it does compound the problem of topology. So things like paths and neighborhoods are harder to follow because you might be jumping all over between different facets, even if things are very close to each other network or topology-wise. So overall, we recommend using this for networks where the nodes can be separated into groups that are meaningful and central to your analysis. So the last kind of node link layout I want to talk about is attribute-driven positioning. Now this is the most strict one as far as placing nodes directly according to their attributes. So this is an example I like to give. This is a billboard I saw in the Reykjavik airport that pretty much shows all the cities that Icelandair flies to leaving from Reykjavik. And even though it's just a map, and most people have seen something like this, it is also an attribute-driven network. Nodes are the cities, and edges are the flights that connect them. But the thing that makes this attribute-driven is that every city is placed on a map according to its latitude and longitude, which are attributes of your city node. So kind of a simple example, but really embodies what it is to position a node according to an attribute. Here's a non-geographic use from a slightly more academic example of attribute-driven positioning, where the nodes are authors, and on the x-axis they're placed according to how many papers they've published. This is a two-dimensional example. I want to give you a one-dimensional example, which I really like, and I think I later touch on a bigger example of this, which is called edge maps. So here you have a bunch of philosophers and how they influence each other. And the way that they're placed on the y is according to time, right? And then if a philosopher influenced another one, there's an edge that connects them, and if it's from, so this one influences this one, so the edge kind of narrows, and then that one in the future, so the edge is kind of rendered differently to show that. And this one relies on interaction. Can you imagine drawing this without interaction? It would just be a sea of edges that would make no sense whatsoever. So this one, when you click on a node, it only highlights the edges that are incoming and outgoing of that node specifically. And then on top of that, you have it sized by the significance of that node, which was computed. So this is an extra attribute that was computed by the authors. So you can see what are the more significant philosophers, and maybe that will make you want to click on them and see who they've been influenced by, and so forth. So this one leverages both on-node encoding and attribute-driven positioning. And because of the fact that you only see edges when you click on them, it's the querying and filter operation that is crucial for this visualization to be usable. So attribute-driven positioning is particularly suited for quantitative attributes. So like the examples that I've shown you, number of papers, year for the first paper, and so forth, or time. Isn't great for visualizing the topology of the network, slight understatement. And it's recommended for small and sparse networks where the relationships between the node attributes are important to the analysis task, and the topological features are really just for context. Now, you might have noticed now a certain trend in when we recommend things, that a lot of times we talk about the task, right? You might get people coming up to me and saying, hey, I have to visualize this multi-thread network, what should I do? And the thing I always tell them is that it depends what you're trying to do with network. The visualization will reflect and will support different types of tasks, so knowing what you want to get out of it or what are the kinds of questions you have are paramount to picking an appropriate visualization. So I want to talk a little bit about, okay, so I've seen these types and now I want to actually use them with my data. What are the tools out there that are available for this? Now, in order to, I think most people in this room would actually definitely fall more in the developer category, but I also wanted to include a non-coding approach. So what are the GUI tools that I can just upload my network and play around things and require no coding whatsoever? This is obviously good for people who aren't coders, but also if you want to just test drive a certain layout, that I need to actually write up all the D3 code for it. So I have these two personas. Maya is the proficient coder, and Brad is the graphic designer. So I'm gonna, as I go through these examples, you'll see here the language that this is in, and then over there on the right, you will see what are the techniques that we've talked about that this tool or library does or doesn't support. Also, I'm pretty sure we'll put these slides up so you don't have to keep notes or anything like that. So we'll start with and I don't know how far along you guys are with your D3 skills by now, probably pretty proficient. So I'm sure you've seen all of the Viz data set, none of the examples, all of my crosstalk stuff, right? So I don't have to tell you, D3 will support anything that you can possibly think of, including our 3 approaches for doing diagrams over there. So this is the Les Mis force-directed layout, so with on-node encoding as an example. Some of you might have heard of Cola.js. So it's a JavaScript library that is this constraint-based positioning, and it's really cool for for example, rendering metabolic layouts or biology systems where you can say, hey, I want everything to be, nobody, who here has heard of Cytoscape? Who here has used the JS? Okay, so Cytoscape has kind of the JavaScript library where you can load it up. Works really well with the D3 graph format, so that JSON that has the nodes and links, you can load it up and it will very quickly do the layout for you. We'll do a lot of the graph traversal stuff, so this is kind of like a library that doesn't require the GUI, and I just used it recently for our last paper, and it was really, really helpful. And I'll talk about the GUI one when we get to Brad. If you use R, which I just recently started using, they have a library called gggraph. It came out just with the latest release just a couple of months ago, maybe 6 months ago, and they have a lot of really cool, very easy one-liners, a lot of different layouts, and you can use for on-node encoding as well as attribute positioning. Does not, as of yet, support faceting on the on-node encoding. In the R Python kind of boundary, we have Plotly, which has wrappers for both of these. Also, so if you're more comfortable with Python, you might want to use this, and which also allows for attribute positioning, on-node encoding. And for example, we'll look at something like this. I do want to point out that when I say it supports on-node encoding, sometimes it's limited to like size and color. I tried when I was making the content for the tutorial at Viz to make all of the networks using like R or for example, some Python library. But when I got to the nested bars encoding and I wanted to do something a little more complex, I quickly ran into the limitations of these libraries. So they're really great for prototyping. Hey, I want to see what this looks like, but I find myself eventually going back to D3 and the JavaScript libraries that give you more control. But for the sake of just understanding what your network looks like, I had when we were testing out different layout algorithms for our user study that we ran recently. So pretty easy to use, really good documentation. If you have any questions, Ilkin worked with a lot of Cytoscape stuff. He is your go-to guy for Cytoscape. And you can generate these things on the fly with zero coding. And another open source one is Gephi. I would say not as popular, but pretty close. So another option for visualizing things without having any coding. And also only supports on-node encoding and attribute positioning. Now, surprisingly, this I actually only realized when I was making these slides, NodeXL, which is an extension for Excel, actually will visualize and facet your network for you, which is good to know, and that's what that would look like. So if you wanted to create a faceting one and the other, and you don't want to go the whole coding approach, you could use NodeXL. By the way, does anyone else think that the XL is impossible to decipher from that logo? Knowing that that's what it was supposed to be, I was like, where's the XL?
Wait, X?
Yeah. Even now, right?
Oh.
I can tell. Okay. We're going to go through tabular layouts, and then we're going to get to the fun activity part. I mean, this is pretty fun, too, but fun. So tabular layouts, these are the three types. Who here has heard, as Alex talked about adjacency matrices? So hopefully everyone raised their hand when I ask who here has heard of adjacency matrices. Who here has used an adjacency matrix? Okay, so a few hands. So the next 2 or 3 slides might be a little boring for you, but who here has used or heard of quilts? Or biofabric? Okay, I will be teaching you something in this section. So we'll start with the adjacency matrix, and the way that I'll do it is I'll go from the node link representation that we were looking at and merge this into an adjacency matrix. So the key idea here is that every node is represented as a row as well as a column. And the way the edges are represented is the intersection between the row and the column. So if these 2 people are married, that would be an edge there. If it's not a directed edge, such as this, then it's also represented at the opposite row and column combination, so you end up with the symmetry between the 2. We were to encode all of the edges in the network we've been looking at so far. That's what that would look like. Notice that the directed edges, so the mother one only shows up once, and the coach one only shows up once, because those are directed. As far as encoding edge attributes directly on there, we already have the label, which is an attribute. But if we want to encode, for example, how often that interaction has happened, you could use the opacity of the cell itself to show the most of the darker ones or the ones that have happened more often or less often. One of the really nice things about the adjacency matrix is because every node is associated to a single row, you can pretty seamlessly associate a table of attributes to it. And you're limited only by as much screen space as you have, what you have. But unlike the on-node encoding, you can just keep adding attributes. So if you want to look at a ton of things at a different time, you can just squish them as extra columns in your table. Another cool thing about tables is that they are inherently sortable. So if we wanted to sort, for example, by who has had the most drinks on the last day, we would see that Tom had 5 beers. And so you can do an attribute-driven kind of layout, which might help with certain tasks. Here's an example of an adjacency matrix in the wild. This is from Moritz Stefano. If you haven't heard of him, he does some really cool stuff. These are cereal ingredients. And how often do they co-occur? And then he clustered them by types, sweets, nuts, and so forth. And you can kind of see how those are organized. And the size of that circle that's in the edge cell is how often that particular combination happens in cereal. And so that's for the edge attributes. And I didn't add them, but if you, for example, had more information, like, I don't know, the nutrition of each one of these, you can imagine just putting a table next to it and being able to do the analysis that way. When it comes to how to encode these edge attributes, I've shown you pretty simple examples, right? Circles, the size of circles, the opacity of the cell itself. There has been a study that looked exclusively at when you have more than one edge attribute. In this case, they're comparing networks, but if you're comparing 2 different networks, or if you have 2 edge attributes on one network, it's the same conceptual thing. And they kind of said, okay, if you have 2 attributes, these are the different ways. And they did a crowdsourced study to see which was the most efficient. Out of curiosity, if you're looking at these, can I get an idea of what do people think they would prefer as far as looking at 2 edge attributes at the same time? I'll give you 10 seconds to look at them and think about what would be the one that would be most amenable to answering tasks on edge attributes. Can I get a show of hands for this one? There's no right, oh, there's a right answer, which is the answer to this paper. You guys know you're supposed to raise your hand. Okay, so 1 hand. 2 more. Ah, interesting. This is probably the first time where most people raise their hand with the right one. So the one that people preferred was this one, which actually took a little getting used to for me. The thing about this one is that with colors, it might even work okay, but the problem is that they can be confounded if they're gray or black with the actual grid lines of the matrix. So imagine if you have 2 bars that are completely full. Let's suppose all of these are completely full. It just looks like a really big cell matrix. So the fact that the lines kind of align with them can be confusing. Yes?
Did they run into issue with the one all around the right with the colors being so close to each other, changing the perception of the color? Like I know that one's black and white. But
So because, like I was saying, the thing that they used this for was for comparing networks. So it is just the relative difference between the 2 that matters. So this one would say that had more than this one. The one on the outside had more than the one on the inside.
Oh.
And so this had the same. And so it really is the hue comparison that made it the most efficient. This is, so I'm focusing a lot on edge attributes here. If you think of node attributes, this is work that Ethan Kirshner did. He graduated a year ago. I keep saying I underestimate it. So he graduated, he did Graffinity, which is flights between different US airports, and the number of flights is defined by the color in the cell. So you can see what are the cities that are most connected, and then for each airport, he had all these different attributes that he put as attributes on the, as a table juxtaposed to the rows and to the columns. 2 more quick examples of adjacency matrices. This is very recent work, came out this year. If you recall when I was talking about matrices earlier, is that when the network is undirected, you're pretty much, it's symmetric. What you have here is the same as here. So you're duplicating information. So what he did is said, okay, I'm going to use half of the matrix to represent topology, and the other half of the matrix, I'm going to compute another attribute. In this case, it's node similarity. So for every pair of nodes, how similar are they according to their attributes? And then I'm going to encode that with color. So it's a nice way of kind of using up that leftover matrix, of course, only for undirected networks, to encode something else about the nodes. And then you juxtapose the node table itself on the right. And the last example I want to give for adjacency matrix is Ilkin's work, which he presented at Viz this past month. It's called TMAX. Has he talked about this here? You guys have not seen this? Okay. So the cool thing about this is that it represents these nodes that have a hierarchy, right? So you have regions that are composed of states, and then you have this kind of macro regions, southwest and northeast. And you can see here in the colors, so the dark blue are the macro regions, and as you go in, the red are the kind of these east, west, south, and then the actual inside, like the green here, is just the states themselves. So you kind of have this representation of the different hierarchical levels of this tree within the matrix itself. So you can kind of get an overview idea here, one level deeper here, and then the real nodes itself are in the middle. This is really cool work that they are working on right I've talked a little bit about ordering, attribute ordering. One of the most important things in order to make any sense from an adjacency matrix is how you order it topology-wise. So you guys might have seen this in your Googling around of code for adjacency matrices or some homework maybe, I don't know. But this is a really cool demo. If you look there on the right, as the user changes the type of ordering and changes the order of the rows and columns, you see completely different structures kind of emerge. And so this really helps highlight the importance of ordering in order to get the most of the topology in an adjacency matrix. This was one of the big criticisms in one of the earlier work that compared node diagrams and adjacency matrices. The authors, and I will remain unnamed, ordered them alphabetically, which is great for if you want to find someone letter D, but it absolutely doesn't help you as far as interpreting the structure of the network. So there are entire libraries such as this one, Reorder.js, that is focused exclusively on how can I order my adjacency matrix in order to bring out these topological structures. So adjacency matrices are really great for dense and completely connected networks because every edge has a little allotted cell. There's no such concept as edge crossing. It does require a lot of space with respect to the number of nodes. And like I was saying, there's a complexity depending on the ordering algorithm that you choose. You can see different things. Overall, we recommend this for small, complex, and dense networks that have very rich node and edge attributes for everything except for tasks involving paths. Paths are pretty brutal to do with adjacency matrices, which we also confirmed in our crowdsourced study that we did 300 people where they did paths on node links, paths on matrices, and they did way worse with adjacent matrices. Actually, some of you might have heard the story. When we were putting together a task for the study, we came up with a path task, but I didn't actually do it on the matrix. I'm like, well, I guess I could try to find what are the Europeans that connect so and so and so and so. And then when I actually had to do it, it was such a pain to do even myself. I was like, oh, I don't know. You know, I'm sure that they can figure it out. And eventually I did it, but the adjacency matrix path following is really not an easy task to do. Okay, I'm going to, so it's 1:10 and we have until 1:45. Okay, so 10 more minutes, I'm going to finish tasks, the tabular ones, and then we'll get into the drawing. So the idea with quilts, like I was saying, is that it only works with, actually I didn't mention this, quilts only works for layered networks, and they're very similar to adjacency matrices. So let's walk through the example here. If we think of these as layers, Mark is in layer 1, and he connected to Sue in layer 2, and you can ignore the friends edge just for now. Sue is in layer 2 that connects to Tom in layer 3, and so forth, and so on. When you have an edge that doesn't connect directly from one layer to the one next to it, it's called a skip link. And I'll show you how Quilts handles that, but it's really meant mostly for completely layered networks. So what we're going to do is we're going to assemble a quilt from this. So we'll put that up there on the top right, and we'll start creating a column with the first node. And what we're doing is we are alternating rows and columns for every layer. So here we have the first layer, and then we bring Sue over as a row, and then we bring Tom over as a column, and we bring memory exercise here, Mary and Cole as rows, and John as a column. So that is the quilt that derives from our initial social network. And then if you remember the skip link, it actually just gets put here to the side. So this is the edge between Tom and Mark. The example from the actual paper that proposed quilts looks like this. So here you have the node link representation on the left and the quilts representation on the right. Doesn't look like it saves that much space compared to an adjacency matrix for a small example, but if I show you a larger example, this is the node link representation, that is the matrix representation, and this is the quilt representation. So it's cool, it's much more compact, and it leverages the fact that inherently with layered networks, you have a lot of white space with the exception of these skip links. So for particularly that kind of network, it is pretty useful. As I mentioned earlier, family trees are a type of layered network, so this is applied to the Simpsons family tree. This is an example from the paper, so this is how they exemplify it here on the left, and on the right you have an example of a much larger historical, I think it's English royalty or something, family tree, also represented with quilts, called Genea quilts, because it's made specifically for genealogies and tilted at a 45-degree angle to save space, which I think makes it a little harder to read, but it is optimal as far as screen space goes. So quilts are really good, as I've said about 15 times already, for layered networks. The problem is that links between, so the skip links that I was talking about, can be problematic both to integrate, and it takes a little bit of understanding to decipher them. So really good for layered or k-partite networks with limited skip links. And the last technique I'm going to talk about is biofabric. Now this one is pretty new. I don't remember what year it came out. I think 2012. I guess it's not technically that new anymore. Not super adopted, but it has a lot of really cool potential. So it's very similar in this, to the adjacency matrix in the sense that every node is associated to a row, but edges are actually drawn by just connecting the source and target. So our social network looks like this with biofabric. Now, much more compact than other representations, but takes a little bit of thinking to understand the actual structure of the network. Now, as you can imagine, because every node is associated to a row, you can very easily associate a table of attributes, kind of like you did with the adjacency matrix. But the true power of biofabric, and actually unexplored, because this was not something that was included in the original paper, is the fact that every edge is represented in a unique column, so you can also add a table of edge attributes. So this is the first approach that I've talked about that is really scalable with respect to edge attributes, because now you're not limited either to the line that connects it in the node diagram, and you're not limited to the cell in the adjacency matrix. You actually have space here. And so this is a really cool way of encoding edge attributes. You can still encode them directly on the edge. So for example, if you wanted to highlight two with color or potentially use the width of the edge to encode a certain attribute. So going back to the Les Mis example, this is what the Les Mis data set looks like with biofabric. So, you know, a little bit harder to interpret, but has its pros. And really good for visualizing rich edge attributes and node attributes at the same time, which might be important depending on the kind of tasks that you're trying to do with your network. A little more difficult to discover neighbors, clusters, and definitely following paths, because you pretty much have to skip over to find where those things connect. So overall, we recommend the small networks that are sparse, that have a lot of node and edge attributes that are relevant to your task. So I want to make tabular representations. How can I do them? D3, JavaScript, will support all of them. So here's an example of the biofabric one that we just looked at. For R, the gggraph one that I showed you earlier also does, and this is super recent. I think it actually looks more aesthetically pleasing than the JavaScript version, and it's a one-liner. So the ggplot for R is really cool if you want to kind of make these very quick prototypes of your data. So this is the biofabric layout with R. R also allows you to do adjacency matrices. So of the three, R just doesn't do quilts. You'll see that the quilts icon is missing from the right. With Python, a bit of a hack. It doesn't actually do adjacency matrices as such, but it does heat maps. So as long as your data represents the edge attribute of interest as a quantitative value, you can make a heat map and call that an adjacency matrix. So I'm going to say that it does support that. Also, surprisingly, supports quilts. And the only reason I know this is because the paper says that they implemented this in Python. So it's not like a one-liner library, it's just possible to do. It does not support biofabric. What does support biofabric is Tableau. And this is kind of recent as well. So you can actually use Tableau to create a biofabric representation of your network. As far as quilts go, there is the tool in the paper, the Genea quilt tool, but you have to download an executable, so it's kind of like very research prototyping. So if you wanted to test it, you could. It's not nearly as user-friendly or as intuitive as like these kind of commercial things like Tableau or R and things like that. And as far as GUI-based adjacency matrices, we have nothing, which is really impressive. I feel like that's a startup right there. There is no way to create an adjacency matrix if you don't know how to code. So you're welcome. So let's use the last 20 minutes to do this activity. So there's two options for the network you guys are going to draw. One is this tool that I built for the visualization tutorial. If you want to draw your own Twitter network, just out of curiosity, can you raise your hand if you use Twitter and have a Twitter handle? So Alex was right. Very few people at the Viz tutorial had a Twitter handle, and then I was telling him, these young kids, they'll all have it, you'll see. And he was like, no, I'm like, the entire class is going to raise their hand. So maybe not. So it's a good thing we brought back up data. So if you want to use your own Twitter network, this tool that I created, so far it's not been super useful. You can go on to bit.ly.Twitter network, put your handle at whatever, and it'll show you the last 5 people that you've interacted with, mentions, retweets. If you would rather use, if you don't have Twitter, or would just rather use this, I'll have my helper here help hand out on that side. So here we have Michelle Obama's latest tweets as of 2 weeks ago when we were at the conference. And so you have the people she retweeted and the people she mentioned and the interactions amongst themselves. Sorry about the size and the resolution of that printout. After I printed it out, I realized it's kind of fuzzy, but I didn't want to waste more paper. So what I want you to do is to pair up. So if you just sit next to one other person, and then we'll start the activity. Oh, raise your hand if you don't have paper, because you're going to need paper and pen. So, okay, raise your right hand if you want pens, and left hand if you want paper. Okay, so the activity is you're going to choose one of the 6 representations that we've talked about today, except for quotes, because the network that you have in front of you is not layered. So I actually should not have included that one here. So ignore that. So any of the other 5, and I want every pair of people to pick one and encode it. You can encode, try to encode as many attributes as you can. I believe that so you definitely should encode the number of tweets, and then the rest is up to you what you want to encode based on the technique that you choose. I'm going to give you guys 15 minutes to draw it up, talk to your partner, how you guys want to do it, and later you're going to have to explain those decisions to make sure that those are thought out. And then we will revisit in 15 minutes. And I'll give you a 5-minute warning when we're 5 minutes away from being done.
Can you go back to the slide to find it?
Oh, yes, absolutely. Thank you. I remember saying that in Auschwitz, really emphasizing accordingly.
People still see what is directed.
I guess you could do that like but there's no
Did you want a piece of paper? I have an extra paper. Oh, you just draw it there? Okay, that's fine.
we're gonna have a few views. One's like a Pokemon cards. One's like 6 Pokemon, so like going to like and then a map where you find and stretch goals.
So we're just starting with some displays. That's